It's been a nerve-wracking month filled with nail-biting deployment sequences for the brand new Space Telescope. And believe it or not, everything worked out as smoothly as it could have possibly been. Remember the infamous 344 single failure points on the telescope? Well, they made it look like these failure points didn't even get the chance to fail. So my sincere congratulations to all the people involved in achieving this remarkable feat. And now that the telescope has arrived at its destination, many wonder what comes next. Why do we have to wait until summer to see the first images? And what will happen in between? For how long will the telescope operate? And why will it point its mirrors toward a lonely star that is 241 light years away? Well, this and more is what we're going to look at in today's video, so let's begin. First and foremost, in order to take a clear picture of the cosmos, the James Webb Space Telescope will need to align its 18 individual mirror segments to form one large 6.5 meter telescope. In order to do so, the telescope will use the help of the primary near-infrared camera, and the mirrors will be pointed at a bright, isolated star, which will actually be the first thing the telescope will look at. The name of this first target is HD 84406, a yellow dwarf that is a lot like our own Sun and is located around 241 light years away from us in the constellation of Ursa Major. Each of the 18 mirror segments will show a different image, which will be blurry because they are not aligned. But it is with the help of these blurry images that the James Webb team will begin the cumbersome process of aligning the individual segments so that they end up working as one single big mirror that is capable of showing crystal clear images. I say very slowly because the whole process will take around 3 months to complete. Why so long, you may ask? Well, because each mirror segment moves at an extremely slow pace, more specifically in the micron and nanometer ranges, which for reference, nanometers can be used to measure the size of particles or even your DNA, so that's pretty small. Plus, they will move one mirror at a time, so no wonder it takes so long. After the alignment of the mirrors has been completed, the telescope will enter the final phases of commissioning and calibration of the scientific instruments while observing representative targets. And the best part is that these representative images will be released to the public as early release observations, showcasing the capabilities of Webb. This whole process of commissioning and calibration will take another 2 months to be completed, marking the 6th month since the telescope left Earth, and the long-awaited beginning of routine science operations that promise to make many new groundbreaking discoveries about the universe during its lifetime. Speaking of which, much has been said about the near-perfect launch of the Ariane 5 rocket that put Webb in a trajectory so precise that much less propellant was actually needed to make course corrections than expected prior to the mission. For reference, the minimum baseline duration of the mission was to be 5 years, but after the successful and precise launch, the James Webb Space Telescope should have enough propellant to allow science operations for significantly more than a 10-year lifetime. Rumor has it that it could go for as long as 20 years. However, we will still have to wait for a few more months until the team has reviewed the data and put an exact number on the telescope's lifetime. But what does propellant have to do with the duration of the mission? Well, even though the second Lagrange point is a pretty stable place in terms of gravitational forces pulling at the telescope, it isn't perfectly stable, and so without a periodic correction, it would end up spinning out of its desired orbit. And this is where the telescope thrusters come into play. In fact, they are the very same thrusters that performed the course corrections while cruising toward L2, and since the trajectory was so precise, the telescope didn't need to fire up its thrusters for too long, thus saving extra propellant that will be required to keep Webb orbiting around the second Lagrange point. So that's why the better the initial trajectory, the less propellant you will then need to complete the course corrections, and so the more propellant available for staying in orbit around L2. And in case you're wondering, it takes Webb about 6 months to complete one single orbit around L2. However, the telescope will have to briefly fire its thrusters once every 21 days in order to tweak its orbit and stay there. Alright, I hope you found this video helpful and could answer some of your questions about the immediate future of the James Webb Space Telescope. I hope to see you all again in the next video, and thanks for being here once again. Have a nice day, take care, bye bye.